All right. So yeah, if you haven't worked on this two continuation, okay, please do it now, okay. Yeah, while you're doing it, okay, so a couple of things, okay. The first is I will have actual office hour, okay, so just right after this class, okay, from 2 until 3 o'clock, okay. So in this case, if you have any questions, okay, so like the practice quiz, okay, or homework, whatever, okay, so please come to my Zoom office hour, okay. And also we have quiz tonight, okay, so from 8 until 11, okay. So you can choose any 30 minutes time block, okay, so to complete your quiz, okay. So just make sure no later than 10:30, okay. So in this case, you have enough time to finish the quiz, okay. So I will keep my Zoom open, okay, just this the Lex room, okay. So if you have any technical question, okay, for example, my laptop is kind of crash, okay, and my Wi-Fi is kind of doesn't work, okay, whatever, okay. So you can log in the Zoom, let me know, okay. So only for technical question, okay. So if you ask me kind of can you give me some hint for this question? No, okay. So and also all right, so any question, okay, please type in the chat window, okay? Type in the chat window, okay? And so how many quiz? So totally 12, okay? So if you did the practice quiz, okay, practice class 12, okay, same amount for the same amount for the real quiz, okay? Yeah, similar difficulty, same types of question types, similar types question, okay? And so after the quiz, okay, so I will go through individual question, okay, for all you guys, okay, because although the program will automatically kind of grade you guys kind of the quiz, okay, but sometimes the program is stupid, and if you miss one long pair electrons, it's your grade kind of wrong, okay. So I may give you back some partial credits, okay. All right, so that's all about the probably I need at least spend 2 days to grade you guys quiz, okay, because we have totally 92 or 93 students. That's quite a lot, okay. Right, you should be able to find it yesterday, okay. So in the same the website, okay, it's Smart Work 5, okay. So it's due practice quiz due last night, okay. So 11:59, okay. Yeah, it's on the smart work, okay. But if you miss the practice quiz, okay, so probably you still can open it now, okay. So but just kind of already showed all your answers, okay. You cannot practice on it anymore. Okay. All right, any question about the quiz? Okay, so if there's no, if you have further question, okay, please come to my the office hour, okay. Please come to my office hour just right after the class, okay. All right, so we practice on these two guys, okay. All right, so for the first one, okay, so DO number is 0, okay, so that's good, okay, no dot bond, no ring, and also no tree bond, okay. That means kind of the pretty much straight chain, okay. All right, so you first draw the carbon framework, 3 carbons, only 1 carbon framework, okay. All right, so next kind of we have 2 bromide, okay, so then the student can begin to random kind of add the 2 bromide, okay, try their best luck, okay. You do it stepwise, okay, okay. First add 1 bromide, okay. All right, so where can you add it, okay? You can add to here or add to here, okay. So that's give kind of the 2 structure, okay. Someone asked how about add to the end carbon? That's the same thing as add the first carbon because that's symmetrical, okay. Right, and then afterwards, okay, you generate kind of the 2 structure, okay. Here, okay. Right, and then falling, okay, we add the second bromide, okay. Do it stepwise. Add the first one first, okay. So for the first structure, you can add bromide here, but bromide here, okay. So all are different, okay, because there's no symmetrical in this molecule. And in this case, we'll generate the 3 structure, okay, based on the first one. All right, good, okay. And then we can move to the next one, okay. Next one, okay, so look like only so like only 2, okay. So this is the same as here, okay, symmetrical, okay. All right, so in this case, yeah, it looks like here we can generate kind of here the 2, okay, another 2. All right, okay. So looks like here based on this formula we can generate 5 constellation, okay. So but you need to double check it, okay, before you submit your answer, okay. You find kind of these 2 is exactly the same thing, okay. So that's unfortunately sometimes kind of you draw the repeating the structure, okay. And so yeah, cross out, okay. So yeah, based on the C6 C3HBr, okay. So only totally 4 constituent isomer. Right. So for the C4 H6, the steel numbers equals to 2, okay. So that means you can have the 2 double bond, 1 triple bond, or 1 ring, 1 double bond, or 2 rings, okay. All right. So did anyone try the C4H6? How many constituent isomer can you draw? Okay. So if you type in the number in the chart window, okay. How many constituent isomer can you draw based on C46? C4H6? 4, okay. Can anyone draw more than 4? All right, keep in mind you can also draw the ring structure, okay? Anyone draw more than 4? All right. So the right answer should be 9, okay? So this morning 2 students report they can draw the 9, okay? That's pretty good, okay? All right, okay, so let's start, okay? So C4H6, okay, so you have to keep in mind it can be ring structure or kind of the linear or branch, okay? Right, and then we draw the carbon framework first, okay? Carbon framework, okay, so yeah, linear one, 4 carbons, okay? And also branched one, right, okay? Because this one has a degree of saturation, can be ring structure, okay? So that means you can build up at least 1 ring, okay? So that's a triangle with 1 actual carbon. Or kind of the square, okay? So this structure will use up here the 1 degree saturation, okay? So 1 ring equals to 1 degree of saturation, right? And then next, okay, so because it's 2 degree of saturation, can we draw 2 rings? The answer is yes. Okay, so that's come to here. Yeah, that's kind of real this molecule, okay? 2 triangle fused together, okay? 2 ring, okay? So this guy will take up the both degree of saturation, okay? Okay, so now we go ahead kind of double bond, triple bond, okay, onto the individual the carbon framework, okay. Right, based on the first one, okay, so we can add the double bond, triple bond, okay, we do for triple bond, okay, either here or here, okay. So in this case, we will have the 2, All right, question? Yeah. All right, so if you have any question, okay, please type in the chat window, okay. Yeah. Right, add the triple bond, okay, so we can add the triple bond here or add the triple bond here, okay. Add to n, the same thing, okay. So 1 triple bond equals to 1 degree of saturation. Right, so that's 1, okay, so keep in mind 180 degree, okay. 2, okay. All right, and then how about the double bond, okay, so double bond because the 1 double bond 1 degree of saturation, okay, so if you for the 2 degree of saturation you need to add 2, okay, so we can add to here, okay, so that's the give you 1 structure, okay, so this one a little bit weird, okay, so 2 double bond next to each other, okay, I label just want to distinguish kind of put the C here, okay, right, so this one actually called kind of alanine, okay, we will learn this guy later, okay. Right, and then someone that kind of can we add to front carbon and then last first carbon bond and then last carbon bond, okay. Answer is yes, okay, so that's give you kind of second one. Right. So in this case here the triple bond 2 degree of saturation, okay. All right. So double bond, okay, ring, okay, 1 degree of saturation, okay. So triple bond, okay, so equals here the 2 degree of saturation, okay. Yeah. So that's we use up kind of this DO2, okay. So you generally kind of the for constituent isomer based on the first carbon framework. Okay. All right, and then second is this branch structure. Okay, so we can add a triple bond. Okay, but the triple bond will break up octets. Okay, so if you add on this bond, so the center carbon will have more than 80 electrons. Okay, and that means no triple bond. Okay, so how about double bond? Okay, so for double bond, okay, so we have to add a pair. Okay, two double bond. Okay, that can use up kind of 2 degree saturation. But if you add two double bond, okay, so also break up octet. Okay, so there's more than 80 electrons for center carbon. Okay. So in this case, we cannot generate any structure based on the second carbon framework. Okay, so that's keep in mind. Okay, no structure. Okay. All right, and then for in case with for the ring structure. Okay, so we already take up 1 degree on saturation. Okay. You need to add another degree on saturation. That's only possibility is kind of one double bond. Okay, so for the first one, okay, so we do this one either. Okay. So this one kind of total symmetrical, okay, so we can add double bond anywhere, okay. So that's give you another constituent isomer. All right, for example, add double bond here, that's fine, okay, the same thing, okay. You can add here, add here, add here, okay. So that's working. And but for the triangle one, okay, because there's kind of no so high symmetrical, okay. So you can add a double bond here, add double bond here, or add double bond here, okay. If you add here, same as kind of left, right, okay, so that's simple, okay. So based on this triangle one, actually you can generate kind of 3 constituent isomer, okay. This, add on the left, okay. Actually, sorry. Left, okay, or add kind of on the bottom. Yeah. So 3 constituent isomer, okay. So in this case, based on this barium one already use up 2 degree of saturation. Okay, so over you can generate kind of 9 constituent isomer. All right. So that's how do you do this question? Okay. All right. So any other questions? No. Right. So if there's no further question, okay. So I'm going to
Can you explain how the second one doesn't count?
1 second. Okay. What's your question?
The second one where there's an X, how come that one doesn't count?
1 second. This one?
Yeah.
Right. This one, okay, you cannot give structure with 2 degree of saturation. All right. So if you want to add a triple bond, give 2 degree of saturation, you have to do this. So that's you break up octets, okay. So you have kind of 10 electron around the center carbon, okay. If you add 2 double bond, okay, you will have like this. Also break up octets, okay. So that's answer is no.
Okay.
Yeah. Someone put here. Okay. Can you show us more time how to get DU? DU just calculation. Okay. So remember. Okay. Yeah. That's some people already list here. Okay. So 2 times carbon number. Okay. And then plus 2 minus 2 and then minus hydrogen. Okay. So that's the easy. Okay. So this point. Okay. So normally DU number calculation. Just worth 1 point. Okay. So those the easy money you need to earn. Okay. So yes, you can do another side, but we will generate the same molecule. Okay. If you do double bond here, do double bond on the top, do double bond kind of on the left. So all these 4 guys are same thing. Okay. So this one you rotate like 90 degrees. Okay. So generate here. Okay. So you further rotate 90 degrees, you generate this one for 90 degrees. Okay. So these 4 are same molecule. Okay. All right. Okay. So if there's no further question, okay. So we'll move to the new maybe get a new page. Don't worry. Okay. So there's no constituent isomer join question in the quiz tonight, okay? But you'll see something in the quiz on next quiz, okay? Quiz 2, okay. All right, so we'll continue the chapter 2, okay? Try to finish chapter 2 today, okay? All right, so next I think we will learn is the physical properties, okay, and then the molecular structure, okay. So physical property are more related to intermolecular force, okay. So it will determine the melting point, boiling point, and the solubility of one molecule, okay. All right, and then before we will learn all these intermolecular force, okay. So first, we will keep a little bit in idea, okay. So keeping in mind, okay. So all these intermolecular force actually based on the charge, okay. So if you have kind of the bigger charge, okay. So and then there will have kind of stronger interaction, okay. And also depends on distance, okay. So if two molecule kind of too far away to each other, okay, that will be weaker interaction, okay. So that's easy to understand, okay. All right, so now let's start, okay. So first intermolecular force is the ion-ion interaction, okay. All right. So ion-ion interaction only happens between two ionic compound, okay. So two ions, okay. And ion-ion interaction is kind of pretty strong, okay, because you have kind of totally the positive charge cation and also anion, okay. So strong electronegativity and electrostatic interaction, okay. One example is sodium chloride, okay. Sodium chloride is melting point the 800 degrees, okay. So that's why it's the high strong interactions, okay. And ion interaction the force is about kind of 188 kind of kcal per mole. Okay, and then next kind of weaker than ion is called ion dipole interaction. So sodium chloride has very high intermolecular force, high melting point, okay, high boiling point, okay. Why it can dissolve in water, okay? You can dissolve the salt in the water, okay? So break up the A and the Cl kind of interaction, okay? Why can we do that, okay? Because the ion dipole interaction, okay? So ion dipole interaction happens between the ion and those the polar molecule, okay? Polar molecule, okay? Polar molecule refers to kind of this molecule has the polar covalent bond, okay, right? So example is the sodium chloride kind of dissolve in water. So sodium chloride, like I said, kind of the very strong intermolecular force, okay. But once you dissolve in water, okay, so there's the ion dipole interaction, okay. The sodium ion, okay, will interact with water, okay. So water has the polar bond. Okay, so that's the water. We know that has the dipole moment and also the polar covalent bond. Okay, so the partial positive charge here, partial negative, sorry, partial negative, and then partial positive on the hydrogen. Right, and then for sodium cation, okay, the oxygen will close to it, okay, stabilize the case. So there are actually kind of more than one water strong the sodium, okay. Eventually, kind of the split away, okay, from the chloride, okay. Chloride the hydrogen, okay, will close to the chloride, okay. Chloride kind of the negative charge, okay. So that's how kind of separate the sodium cation and also chloride anion, okay. Right. So next one, okay, is the dipole interaction, okay. Right. So for dipole interaction, only happens between the two polar compound, two polar molecule. Okay. All right. So as long as there's the polar covalent bond, okay, so there's possibility for the dipole interaction, okay. Give you example is the formaldehyde, okay. So formaldehyde is actually kind of very small molecule, okay. So normally for the other molecule with similar molecular weight, okay, so will be a gas, okay, but the formaldehyde actually kind of liquid, okay, right? So the reason for that there's a dipole interaction, have to hold two molecules together, okay. So for formaldehyde there's the CO, the polar covalent bond, okay, so partial positive charge, negative charge on the kind of oxygen, positive on the kind of the carbon, okay, same thing here, positive, negative, okay, and then in this case, we can have somehow kind of the attraction to each others, okay, and then that's the dipole interaction. Okay, a little bit higher. Okay, so next one is the induced dipole interaction, okay. So this intermolecular force is not so common, but we do see it, okay. Induced dipole happen between the polar molecule and also non-polar molecule, okay. The non-polar molecule normally don't have any kind of the polar covalent bond, okay. In this case, hard to get kind of interaction with the polar molecule, okay. But they can be induced to follow temporary the polar covalent bond, okay. So one example is the iodine can have a little bit solubility in water, okay. So right. So iodine molecule just get two iodine atom, okay. So whole molecule is kind of non-polar, okay. So just the non-polar covalent bond, okay. But the can have a little bit solubility in water, okay. The reason for that, okay. So in the water, okay. So that's water molecule, okay. Water has the some dipole moment, okay. So like this way, okay. Positive, negative. Right. And then they see the partial the positive, okay. So or maybe partial negative, okay, can induce the charge separation on the iodine, okay. So iodine has a lot of electrons surround kind of the nucleus cases, or circulate all around, okay. But because they are under influence of the water, okay, so you can generate kind of the temporary charge separation, okay. So a more positive charge on the right the iodine, and then more negative charge on the left iodine, okay. Right. And then they can have some kind of interaction with water. So in this case, the iodine can dissolve in water somehow, okay. Okay, and then move to next one. So the last one, called the instantaneous, dipole impulse, the induced dipole interaction. Okay, so normally I like to call it what's iodine itself is non-polar, okay, non-polar, okay. But you can induce because that's why we call this kind of induced dipole, okay. So you can induce the dipole separation, okay. Charge separation, induce kind of dipole moment, okay. So that's why kind of induced dipole, okay. So all right. And then same thing kind of the for the London force, okay. So London force kind of instantaneous kind of the dipole induced dipole interaction, okay. London force. All right, okay. So only happen between the two non-polar molecule, okay. Yeah, between two non-molecule, okay. All right, so we still use iodine as example, okay. So iodine, okay, itself is kind of non-polar, okay, and then there's another iodine, okay. But the iodine whole thing, okay, so it's kind of solid, okay. That means kind of they have a little bit of attraction between the iodine molecule, okay. It can kind of become solid, okay. All right, and then how that happened, okay, because there's a lot of electrons, okay, just kind of all around, okay, for individual, okay. And at a certain time, okay, so that's why I call it instantaneous, okay. There's the temporary charge separation, temporary charge, okay. So for example, okay, at maybe the 1 of the millisecond, okay, so there's the more negative charge on the left iodine, more positive charge, okay, on the right iodine, okay, just very temporary, okay. So well, that's why called kind of instantaneous, okay. Temporary kind of charge substitution, okay, and immediate kind of induced charge substitution for the neighboring iodine molecule, okay. So neighboring iodine, okay. So now you have a positive, and then I will have kind of negative, okay, on the left, and then positive on the right. So that's the very short, okay. But this interaction kind of enough to hold these two iodine molecule, okay, and then make it solid, okay. All right, and then for the last three, okay, so dipole, and also dipole induced dipole, and also London force, okay. So those three belongs to van der Waals force, okay. Van der Waals force. Van der Waals force, okay. So and so for our organic molecule, okay, okay, so normally don't have the ionic the bond, okay. So in this case the for organic molecule, okay, those three kind of dominant, okay. So that's but for the van der Waals force, okay, so that's a very weak interaction, okay. And so van der Waals, okay. So only the 0.5 to 5 kcal per mole, okay. All right, so in this case if you compare it with the ionic bond, okay, one ionic bond can more than 100 kcal, okay. So the 1 to 4 force, okay, so only 0.5 to 5, okay. So that you can clearly see kind of very weak the interaction for the 1 to Waals force, okay. Okay. All right. So there's another intermolecular force called the hydrogen bonding, okay. So so this guy actually we can see kind of somehow belongs to kind of the dipole interaction, okay. So but it's very special, okay. So we can kind of 6, okay. And but it's stronger than normal dipole interaction, okay. Happen if you have a hydrogen attached to a strong electronegativity atom, okay, like oxygen, nitrogen, and fluorine, okay. And then this hydrogen can also have some attraction with another strong electronegativity atom, okay. So scale strong, okay. I will tell you kind of what's the strong scale, okay. All right, so give you one example, okay. So the HF, okay. And then this hydrogen can have some kind of interaction with the fluorine, okay. And so that's the weak, okay. Right, so and then but the hydrogen bonding is kind of stronger than normal 1 to 4 force, stronger than normal the dipole moment even, okay. Right, because the hydrogen is small, okay, can get close to the heat atom, okay, like fluorine, oxygen, and nitrogen, okay. So you can have a close distance and then shorter distance, stronger interforce, okay. Right. Someone asked kind of how strong is kind of the hydrogen bonding, okay. So normally about 3 to 8 the kcal per mole. Still pretty weak, okay, but relatively stronger than the 1 to 4 scale and also the dipole interaction, okay. So so if there's the hydrogen bonding in the one molecule, okay, so normally has a little bit higher bonding point, melting point, okay. So like water, okay. So water has little bit the higher melting point, okay, bonding point, okay. So bonding point 100, okay, than the normal organic molecule, okay. Dipole interaction, so weaker ion. That's right, okay. So dipole interaction kind of weaker than the ionic, okay, but the stronger than London force, okay. So London force pretty much nothing, okay. I would say kind of less than 1 kcal per mole, okay. Yeah, but yeah, depends on the situation. I'll explain it later. Okay, yeah, that's right. Okay. So yeah, except hydrogen bonding. Okay, so all other 5. Okay, so all other 5. Okay, so yeah, interaction. Okay, the bond strength. Okay, so yeah, goes kind of down. Okay, so like this direction. Okay, strong ion followed by ion dipole. Okay, ion dipole kind of we call it the moderate the intermolecular force. Okay, so yeah, and then dipole induced dipole downward force kind of pretty much nothing. Okay, just nothing. All right, those are pretty good questions. Okay. All right, so next, okay, so all right. So next, okay, we move to the melting point and also boiling point. Okay, after we learned all this the intermolecular force. Okay, so there are some kind of 3 trends for the melting point. Okay, first increase with strong intermolecular force. Okay, so that's easy to understand. Okay, so you have strong intermolecular force, hold molecule together tightly, and then you have higher melting point. Okay, and then here's this example. Okay, sodium chloride. Okay, with ionic interaction, and then melting point 800. And then next, this one called the butanol. Okay, and so only has dipole interaction. There's the dipole polar control amount minus 99, and 14 kind of these 3 molecule. Okay, so especially the first 2 only has only have the London force. Okay, so you can see kind of very low melting point. Okay, so minus 190 minus 130. And the second trend is the higher molecular weight molecule has a higher melting point. Okay, so only for the same type of molecule, same kind of intermolecular force. Okay, all right. So example showed here. Okay, so this one has the propane. Okay, propane has 3 carbon. Okay, and then next is kind of pentane. Okay, pentane has 5 carbon. Okay, pentane has a higher molecular weight and then higher melting point. Okay. So that's can be understand if you have the higher molecular weight. Okay, so then you have kind of more interaction. Okay, so more interaction surface. Okay, Okay, and then you have kind of the stronger intermolecular force. Okay, and then higher melting point. Okay, and the third trend is very interesting. Okay, so if you for similar molecule. Okay, so more symmetrical one. Okay, more branch. Okay, more branch molecule will have a higher melting point. Okay, so we use this linear pentane. Okay, so 5 carbon compared with this branched kind of pentane. Okay, so also 5 carbon as example. Okay. So the linear one has the minus 130-degree melting point. Okay, but this branched one. Okay, this star shape. Okay, minus 70. Okay, so the branch one actually has higher melting point. Okay. So why is that? Okay, so because this branch one is more symmetrical. Okay, and then easy to pack into kind of a tightly structure. Okay, so you can compare with the building block. Okay, so when you are young. Okay, so you play the building block. Okay, use the building block to build the castle, kind of the building, whatever. Okay, all right, so always you use the unit is some kind of square or kind of some triangle. Okay, very symmetrical one. Okay, and then that's very stable, can build up kind of the very huge kind of the castle. Okay, but no people use some kind of just single line or some kind of some kind of the rope. Okay, whatever. Okay, so linear the building block to build castle. Okay, because those not so stable. Okay. But I guess you guys kind of too young. Okay, so you guys only play the Lego. Okay, no one play the building block. Okay, so all right. Okay, and then the boiling point. Okay, so the 20 the first 2 are same as the melting point. Okay, so stronger intermolecular force. Okay, and then you have higher boiling point. Okay, and here is the example. Okay, so sodium chloride. Okay, has higher boiling point than the other. Okay, so include some the polar compound. Okay, so that's easy to understand. Okay. And then the boiling point increase with molecular weight. Okay, similar like the melting point. Okay, so because just use kind of the group 7 example. Okay, so iodine, bromine, and then chlorine, and also fluorine. Okay, so chlorine and also fluorine is gas. Okay, bromine is a liquid, and iodine is a solid. Okay, so why is it like this? Okay, because they have kind of higher molecular weight go this trend. Okay, and higher molecular weight, higher kind of the polarity, and then the higher boiling point and higher the melting point. Okay, the reason for that kind of short kind of polarizability. Okay, so so you have kind of electron either kind of the polarized. Okay, so gets kind of temporary the charge separation and the higher London force. Okay, for the iodine and the bromine. Okay, but for fluorine. Okay, so the electrons just strong kind of too close to the nucleus. Okay, not easily get charge separation. Okay, and then that's not easily get kind of strong intermolecular force. Okay, so that's if you still don't understand, just remember. Okay, same kind of the structure, but the higher molecular weight, the higher kind of melting point and boiling point. Okay, right, and then last kind of next trend kind of somewhat different, just opposite from melting point. Okay, it's if the molecule is kind of linear structure. Okay, that's your higher boiling point. Okay, and this time if you have a branch structure. Okay, so then you have kind of actually the lower boiling point. Okay, an example showed here. Okay, so we still use a pentane example. Okay, so remember the linear pentane has the high melting point. The branched one has higher melting point than the linear. Okay, but when we come up the boiling point, it's opposite. Okay, the linear has the higher boiling point than the branched one. Okay, so why is that? Okay, so because the linear one you can pack the molecule close to each other. Okay, and then you can have kind of the higher the interactions. Okay, higher interaction surface. Okay, and then you have higher kind of the intermolecular force and the higher boiling point. Okay, branch one. Okay, so you cannot make two molecules close to each other. Okay, so I just draw you some kind of thing like this. Okay, so for the linear one. Okay, you can pack the molecule like this. Okay, right, so they have kind of pretty close interactions and then stronger molecular force and then higher boiling point. Okay, but for the branch one. Okay, right, so that's not easy to pack close to each other. Okay, so probably you only kind of the two terminal can close to each other, but not whole molecule. Okay, and in this case if you cannot pack them together and then the weaker interactions. Okay, so that's something keep in mind different from the melting point. Okay, so branched one has the lower boiling point and the linear one has the high boiling point. Okay. Last one. Okay, so if for one molecule there's the hydrogen bond. Okay, and then this molecule will have kind of higher boiling point. Okay, so show the example showed here. Okay, and this one is the butanol. Okay, butanol. Okay, it's alcohol. Okay, there's the hydrogen bond. Okay, but for this one. Okay, it's aldehyde. Okay, so there's no hydrogen on oxygen. There's no hydrogen bonding. Okay. And you can see the both have similar structure, but the alcohol has the higher boiling point. Okay, so because of hydrogen bonding. Okay. Right, so for the solubility. Okay, pretty easy. Okay, just one word. Okay, like dissolves like. Okay, like dissolves like. Okay, so polar compound can be dissolved in the polar solvent, and the non-polar compound can be dissolved in the non-polar solvent. Okay, right. Example showed here. Okay, sodium chloride can be dissolved in water. Okay, because sodium chloride is polar and water is also polar. But sodium chloride cannot be dissolved in the pentane. Okay, because one is polar, one is non-polar. Okay. And similar thing. Okay, so pentane can also cannot mix with the water. Okay, because the water is polar, pentane is non-polar. Okay, just two layers. Okay, right. And so there's some kind of special words. Okay, so first one is the miscible. Okay, so that means the two liquid or maybe kind of two solvent can mix in any portion. Okay, and the example is this is ethanol. Okay, so ethyl alcohol. Okay, and water. Okay, so these two both are polar. Okay, in this case they have kind of similar interaction force. Okay, intermolecular force. Okay, they can mix in any portion. Okay, so that's what we call kind of miscible. Okay. And hydrophobic and hydrophilic. Okay. So hydrophobic means kind of one molecule. Normally it's non-polar compound. Okay. Non-polar compound has a non-polar covalent bond. Okay. And then heat water. Okay. Cannot dissolve water. Okay. That's the hydrophobic. Okay. In another end case, hydrophilic. Hydrophilic is molecule kind of has the polar bond, okay, has strong interaction with water, can be dissolved in water, okay, so that's called kind of hydrophilic. And then last one is kind of amphiphilic. Amphiphilic for one molecule, okay, so amphiphilic molecule has both the hydrophobic part and also hydrophilic part, okay, so that's make this molecule somehow can dissolve in water and also has a strong interaction with the non-polar organic molecule, okay, solvent, okay. So pretty quite often used in some surfactant or some kind of the soap or some kind of detergent. Okay. All right, okay. So now we move to the last the chunk of today's lecture. Okay, so it's the functional group. Okay, so functional group is the a way to classify, okay, so try to put the organic compound, okay, into different category, okay. So we have millions of organic compound, okay, and then we use functional group, okay, to classify their kind of the properties, okay, physical property and also organic chemical property, okay. So the definition is the atom or group of atoms, okay, within molecule, okay, show characteristic of a set of the physical and also chemical properties, okay. For example, show for this bunch of molecules, so they have kind of different sizes, okay, some quite small, okay, like methanol, okay, some quite kind of big, okay, like vitamin A, okay, but all of them have the OH, okay, group, okay, so OH, okay, and in this case, they have some kind of similar physical property. They probably has the certain solubility in water, okay. And also the very similar kind of chemical property, okay? And then they can also do same reactions, okay, that we will learn in organic chemistry too, okay. So in this case, we can see all these the compound belong to one group of the compound, okay. So those group compound all have the OH group, okay. So those compound we call the alcohol, okay. So alcohol, okay. Alcohol is compound that contain OH group, okay, also called the hydroxy group, okay, hydroxy group. All right, okay, so now, you guys can take off your the lab notebook and also the pen, okay? Please follow me, okay? So here, a lot of things you need to memorize, okay? All the different the organic kind of functional group and their classification, okay? All right, so we have to learn them one by one, okay? The first is kind of for the organic compound, there are kind of two big group, two big branch. One called the hydrocarbon, okay? Another is the heteroatom compound, okay? So hydrocarbons, okay, only has the carbon hydrogen, these two atoms, okay? And under the hydrocarbon, okay, so another two big group, okay? So one called kind of aliphatic compound, okay? So aliphatic compound include the alkene, okay? Alkene, okay. So alkene is kind of saturated, okay, has the only carbon-carbon single bond saturated molecule, okay. And if there's the carbon-carbon double bond in the molecule, we call it the alkene, okay. Alkene is just the double bond, okay, see that bond, okay. So if there's the carbon-carbon triple bond in the molecule, we call it kind of alkyne, okay. Right, okay, so alkene has 1 degree of saturation, alkyne has 2 degree of saturation. Okay, so that's what we just learned. Okay. And then there's one special the group of the aliphatic compound, cyclic compound. Okay, so could be the 3 membrane, 5 membrane, 6 membrane, even the higher member kind of the ring structure. Okay, so those molecule also has 1 degree of saturation. Okay, all right, and then under the hydrocarbon, there's another big branch called kind of the aromatic compound. Okay. Aromatic compound. Okay. So this compound is also ring structure, okay, but in the ring, okay. And then there's the double bond, okay, followed by single bond, double bond, followed by single bond, okay. So there's kind of alternating kind of double bond, single bond arrangement, okay. Double bond, single bond, double bond, single bond, double bond, single bond, okay. So although it's also in ring structure, but this type of molecule have more special kind of physical property and also have special kind of the chemical property. Okay? So different from the regular ring structure. Okay, so that's why we put kind of a different category. Okay, so we'll learn some kind of the special kind of reaction and those physical property, okay, for the aromatic compound, okay, later, okay, stage. Okay, all right, and then for the alkene, okay. alkene, this one, okay. So if you remove one hydrogen, okay, and then you generate here alkyl group, okay. So alkyl group is very general kind of name for the certain functional group, okay. So it's ready attached to some other atoms, okay. So normally we alkyl group kind of label like this, okay. So just straight line. Sometimes people also put the waving bond, okay. So that's also normal, okay. So that's alkyl, okay. So alkyl is kind of very general the name for certain types of functional group, okay. For example, methane, okay. CH4, okay. So this is 4, okay. So if you remove one hydrogen, okay, that's become kind of methyl group, okay. So methyl group is the one of the alkyl group, okay. So belongs to alkyl group, okay. Next is kind of the haloalkene. So haloalkene is just the replace one of the hydrogen on the alkene with the hydrogen, okay. And if it's kind of fluoro, okay, so fluorine will become fluoroalkene, okay. If we have the chlorine, will become chloroalkene, and then bromoalkene and also iodoalkene, okay. Right. So for example, we replace one hydrogen under the methane, okay, with the chloride, okay. That's become now the methyl chloride, also called chloromethane, okay. So for the haloalkene, there's kind of the common name of alkyl halide. Quite often I just see the alkyl halide, the same thing, okay. So fluoroalkene become kind of alkyl fluoride, okay, and the same thing for the alkyl chloride, alkyl bromide, and also alkyl iodide, okay. Right, and actually you can replace more than one hydrogen, okay. So under the alkene with the chloride or bromide or iodide hydrogens, okay. So for example, if you replace two hydrogen under the methane, okay, so kind of two chloromethane, okay, so also called methane chloride, okay. This is one of your most common organic solvent, okay. If you replace three hydrogen with the chloride, okay, you generate trichloromethane, okay. That's is chloroform, another the very common organic solvent. Right, alcohol and ether, okay. So alcohol we just landed, okay. So that's the alkyl group attached kind of OH group, okay. So that's alcohol, okay. And one example is methanol, okay. So we just landed in the use it here in the lab last week, okay. Methanol, okay. Also called methyl alcohol, okay. And similar structure is the ether. Ether is the two alkyl group attached to center oxygen, okay. So see difference, okay. So alcohol kind of the one hydrogen, one alkyl group, okay, attached to center oxygen. Ether is two alkyl group, okay. So one example the dimethyl ether. Right. And then following is the amine. So amine compound has the carbon chain or alkyl group, okay, or hydrogen attached to the center nitrogen, okay. Depends on how many the alkyl group, how many hydrogen, okay. So if there's only one alkyl group and then two hydrogen, okay, then you generate kind of primary amine, okay, primary amine, okay. So that's labeled like this. If there's there are two alkyl group and then one hydrogen attached to center nitrogen, okay, that's secondary amine, okay. If no hydrogen, only alkyl group attached to center nitrogen, okay, so then we call it the tertiary amine, okay. An example showed here, okay, this is the primary amine. This is actually kind of we call it the methylamine, okay. So this is kind of the dimethylamine, okay. So secondary amine, and then tertiary amine, okay, three methyl group, okay. And then there's another compound called kind of nitro compound, okay. I just kind of label as nitro, okay. So this one just kind of the nitro group, okay, NO2 attached to kind of nitrogen, okay. So that's nitro compound, okay. Pretty easy, okay. Here's kind of nitropropene, okay. So NO2, okay, attached kind of the propene, okay. So now we move to the carbonyl compound, okay. So for carbonyl compound, okay, so all have the CO double bond, okay. But depending on what attachment on the carbonyl group, okay, so you can have be kind of aldehyde, okay. So aldehyde you have kind of here one alkyl group, okay, and then one hydrogen, okay, attached to center the aldehyde group, okay. So that's here like this structure, okay. So yeah, R and CH, okay. And the comparisons the ketone. Ketone has the two alkyl group attached to a center carbonyl group, okay. So for example, the acetone, okay. So acetone we learned in the organic lab, okay. So use it in the organic lab to clean glassware, okay. That's the belongs to a ketone. Right, and next is the carboxylic acid, okay. And it's a derivative, okay. So we'll all learn them kind of all together here, okay. Because they all have the similar group, okay. So this one we call kind of carboxyl, okay, group, okay, carboxyl group, okay. So for the carboxylic acid, okay, so this the carboxyl group, okay, so attached to kind of OH group, okay. So that's the carboxylic acid, okay, OH, okay. And then if we attach OR group, okay, so alkyl oxygen onto this the carboxyl group, okay. So that's become the ester. Okay. And if we attach kind of chloride onto this carboxyl group, okay, becoming acid chloride, okay. So actually you can extend this naming, okay. So if we have the bromide attached here, okay, that's become the acid bromide, iodine attached here, acid iodide, okay. So that's same thing, okay. Right, so last line, okay. So if you have the amide, okay, attached amine, okay, attached to the, so this can be kind of NH2 or kind of NHR or kind of NR2, okay. So it doesn't matter, okay. So so that's become kind of the amide, okay. And then if there are kind of two carboxyl group, okay, attached to center oxygen, okay, two, okay, so and then this one we call the acid anhydride. Right, okay. Here I want a little bit pay attention to amide, okay. So amide that's amine, okay. If the amine attached kind of carbonyl group, okay, you cannot call it amine anymore, okay. This become kind of amide, okay. So that's a common mistake, okay. So so you kind of only see kind of the nitrogen, okay. That's to be kind of amine, okay. But that's wrong, okay. Has to be kind of if the amine attached kind of the carbonyl, okay. So that's become amide, okay. So so this is amine. This is amide, okay. So see difference, okay. So each time we have at least 3 or 4 or maybe more students kind of make mistake, okay. So treat amide as amine, okay. Right, last one, okay. So sorry, a little bit the extension, okay. So put on here, okay. So if alkyl group attach kind of CN triple bond, okay. So this guy we call kind of nitride, okay, nitride compound, okay, nitride. Okay. All right, okay. So that's we done the lecture today, okay. So I know it's kind of a little bit too much for you guys, okay. Unfortunately, that's organic chemistry, okay. So try to memorize all these functional group, okay, and then memorize their name and also their kind of the structures, okay. So there are the very good table on the textbook and 2.6, okay. So try to remember it, okay. So all right. So we done the lecture today, okay.
Thank you, Leo.
RQ is just okay. Just the word general name for certain functional group, okay. So if you have kind of the king, okay. All right, we know that kind of just just kind of the carbon hydrogen, okay, saturated, okay. So and then if you take one hydrogen away, okay. Right, so that's this king will ready to bond something else because you take one hydrogen away, okay, and then that's become the RQ, okay. Right, so that's the word general name, okay. For example, okay, so if you have kind of the methane, okay, CH4, okay, so you take one hydrogen away, okay, become kind of a methyl group, okay, And if you have kind of the C3, okay, so that's we call the ethene, okay. So if you take one hydrogen away, okay, become kind of C3, CH2, okay. So this is called eth, okay. Both belong to kind of alkyl group, okay. So that's one general general kind of naming for the certain functional group, okay. So can you show how to pull up the quiz? Right. So for the smart work, okay, so as long as you know how to do the homework, okay, that just kind of show up as same the website, okay. So let me see, I should have here, okay. So all right, so you line, okay. Right. So that's my interface, okay. So for you guys, okay, probably only see kind of getting familiar and then practice quiz and those the homework one, okay. So tonight, okay, so I will turn on quiz one, okay. So this one, okay, and then you should able to see you in your smart work file, okay. Yeah, that's right, okay. Yeah, use this website, okay. Yeah. All right. So do you guys have any questions? All right. Yeah. Anyway, okay. So I have office hour. Okay. So from now until 3 p.m. Okay. So if you have any question, okay. So you can still keep your Zoom open. Okay. Keep your still Zoom open. Okay. Ask me. Okay. Yeah. You have a good one. Okay. Thank you. Yeah. Oh, lab this week. Yeah, that's right. Okay. Lab this week here, you only take a melting point and also the matter mass, okay? So come in the line up time slot, okay? So line up the lot already post online, okay? So 20 minutes for each person. Okay. Yesterday quiz already closed, okay? Because the due date is the 11, okay? But I think you still can see it, okay? So I don't know, okay? Let me see, okay? It still keep open, okay? But the only problem you cannot practice on it, okay? Because they are already past due date, okay? Let me see. Okay, maybe share screen with you guys. Yeah. So that's still open, okay? So published, okay? So you should see the practice quiz, okay? But the probably you cannot practice on it, okay? But you can see the what kind of the question, okay? You will see in quiz one, okay? What's our okay? IDs here, okay? 424797, okay? So those are the ID, okay? So you need when you open you purchase your smart work account, okay? So once you purchase the key and then probably the programmer will ask kind of what's your student set ID, okay? So you type it in, okay? And make sure check it, okay? So our course title is Winter 2021 CH the 315 underline live, okay? So that means you get the right one, okay? Yeah, all right, thank you. Office or and class and same Zoom link. Yeah, that's right, okay. So that's why I keep it open, okay? So this just the same link as the office hour, okay? So from now until 3, okay? So if you have any question about your practice or kind of homework or kind of any help for the need for the quiz tonight, okay? So you can come in, okay? All right, okay. So that's we done the class today, okay? So let me turn off the